Alright guys, welcome back to the YouTube channel. In this video, we are told to determine the crystal structure, the indices of the plane producing each peak, and the lattice parameter of the materials. So we know our lattice parameter to be A, so we are told to find it. Then given our peak index, right, we are now supposed to give them our HKLs, which are like the 3 units, things like 111, the plane, the direction, 111, 110, all of those sorts, sorry, 111, 110, 211, and so on and so forth. Then we have to determine the crystal structures, the FCC, BCC. So as you can see here, we are giving clue of each indices that falls under each crystal structures, right? So I gave myself the liberty of solving ahead, but I'm going to explain what I did just to save time, because I wouldn't want to be punching calculator for looking for signs on calculator while I delay us. So this question can always come in two ways, guys. The first is this way that you are seeing on the screen presently, whereby they give you the peak index and they give you the 2 theta. Remember, when it comes to X-ray diffraction, you are concerned about 2 theta. Sometimes you will solve and get your theta, and by the time they ask you for the X-ray angle, don't give the answer of theta. Find your theta, then do 2 times theta. 2 times theta is all that is required when it comes to X-ray diffraction. Yeah, so this is the first way I said this question come. It comes in a table where they give you peak index and they give you 2 theta. So you are supposed to look for every other thing by yourself, and this is the other way by which this question comes, right? I'm going to solve both and there will be different videos. So in this one, you can see this graph right here, right? So this graph you're seeing right here, you'll be given only this graph. So from this graph, you get to pick out your peak index and you get to pick out your 2 theta. So can you see your diffraction angle? Exactly. Diffraction angle is 2 theta. Diffraction angle is the main thing that we need when it comes to X-ray diffraction. You don't need theta, we need 2 theta. So sometimes when you solve for your theta, don't give the answer as theta, you need to multiply by 2. So how do we do this? What we do is, when you see this kind of table, we know our peak by saying this is 1, 2, 3, 4, 5. Sorry, this is 5. This is our 6. This is our 7. This is our 8. This is our 9. Yes, all of those peak you can see are our peak indexes, right? So as you can see here, I have 9 peak indices right here. Then you begin to reach each angles that this thing fall under. So if I zoom into this right now, if I trace this down here, sorry, so by the time I trace this down here, right, this is 35, and I know this is not half, so I know it's either 32 or 31.5, but I'm going to just go ahead and choose 32, right? Can you see? That's what I picked here. So you check them one after the other, then you get to pick out your diffraction angle, which is 2 theta, and you get these two values by yourself, which is your peak index and your 2 theta. Like I said, when it comes to X-ray diffraction, all you need is, when it comes to X-ray diffraction, all you need is your diffraction angle. So this diffraction angle is what we're going to use to find every data. So let's go back to the question we are here to solve. Yeah, so solving on for this question, we are being given our diffraction angles already, which is 2 theta. We are given them already, which is this guy, sorry, these guys. So the first thing we want to do, sometimes you might go ahead and begin to divide them by 2 to have your theta, right? So if I was going to divide by 2 to have my theta, right here I'll be having 10.10. Sorry, I think my ink is too thick. Reduce. Can I see this? Okay, yeah, it's better now. Yeah, so right now in this place I'll be having 10.10, right? Here I'll be having I don't know, here I'll be having 25, sorry, excuse me. Here I'll be having 25.45, which is not going to save time. So all I just do is, the main thing I need is my sine square theta. So I go into my calculator, I type sine, right, which gives sine and open bracket. I put in my angle, which is 20.20 over 2. Not just 20.20, I did my over 2 because now what I'm looking for is sine theta, not sine 2 theta. So divided by 2, right, which is this, you can see here, right, divided by 2, then square outside here. This is what you're going to type into your calculator. Please take note of that. So by the time you type that, you get this value, right? You get this value, then you do it for this also. All you just do is erase this from your calculator, then put 28.72, right? Then you get this. So you keep doing that repetitively until you get all of your figures. That was what I said I had to do mine before I start this video, so I can save time and not bore us by just going back and forth. So here in this tab, you can see that I said the next thing we are going to do is we are going to take each of our answers here, right? We are going to divide each of them by the lowest of them all, and the lowest is always our pick one, which is this guy, right? So by the time I begin to use it to divide, I know I pick for my pick one, I say this 0.0308 divided by 0.0308, my answer is going to be 1. So the next one, which is 0.0615 divided by 0.0308, which is my smallest of them all, right? I'm going to get 1.9, yada, 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 but I'm just going to go ahead and approximate, which will give me 2, right? Because all we need is a whole number. We don't need decimal. I approximate and it gives me 2. So I go ahead also here, I say 0.092 divided by my lowest, which is 0.03, I get 3. So continuously like that, I continue to do and I get to approximate. So I'm getting 4, 5, 6, 7, 8. Yeah. So guys, this is where I want you to pay attention. Whenever you find this thing, always pay attention for the digits. Sorry, this is also too thick. Yeah. So always pay attention to number 7. This guy, we don't want him in whatever we are doing. Why is it that we don't want him? Let me explain. So now our HKL, right? Or let's say h square KL square. So when I say 2 square plus 2 square, right, plus 1 square, that is 4, 4, 1, which gives me 9. So there is no way you can generate something with 3 squares, sum of something with 3 squares and get 7. Okay, some of you at home are saying I'm smart, I can do this. So 3 square plus 1 square plus 0 square, this is 9 plus 1, which is 10. Let's try again. 2 square plus 1 square plus 0 square, this is 4 plus 1, which is 5. Okay, 2 square plus 2 square plus 1 square, right? Or that's gonna be 8, 9. Oh, we've done that before. Okay, let me just erase this. Let me erase this and say 1 square, right? So which is gonna be 4 plus 1 plus 1. It falls on 6. Sorry, plus 1, which falls on 6. So there is no way we are ever gonna derive the digits for 7. So that's why you should always look out for 7. The moment you see 7, what you want to do is you want to multiply all your figure by another figure. So for this one, right, since I have numbers that are whole, I can go ahead and multiply by 2. There are cases where you have to multiply by 3. There are cases where you have to multiply by 3 point something 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 something. But because my number here is whole, if the numbers here were like 1.9, 1.8, or sorry, 2.8, 2 point this, now if I multiply by 2, I'll still be having decimal points. So sometimes what I do is I know that if I continuously multiply 2 by all these things, I'm going to be getting decimal number. I think somewhere here, if I multiply 2, I should have 3.98 or something. So what I do sometimes is, I know my goal is to derive at 4, a whole number here. So the first thing I do is I say 4 divided by 1.99. So when I do that, I get 2.01. So I'm going to multiply all through by this 2.01, so that when I multiply it with this, I'm going to get 4 directly. I don't have to be approximating. So that's why I said, first of all, you want to multiply by 2, you want to multiply by 3, you want to multiply by 2 point something, 2 or 3. So now some of you might be wondering, asking yourself that when do you multiply by 2, when do you multiply by 3? I'm going to show you an example right now. So in this place, if I multiply by 2, here I get 2, right? Let me change my ink, sorry. If I multiply by 2, I get 2. If I multiply by 2, I get 4. If I multiply by 2, I get 6. Cool. So this case, I have to continuously multiply by 2. It works. 10, 12, 14, and 16. So now this is perfect. So for the case of knowing how to never apply multiplication by 2, this is it. This is a situation where you don't ever multiply by 2. You need to multiply by either 3 or another figure. So as you can see, I already specified, helping us to understand what I use in multiplying, which is this guy, right? So I'm going to go ahead and erase this now. So again, like I said, let's assume when we're multiplying, we had 2, 4, 4, 5, 6. So at this point, seeing these two guys, and there's no way I can approximate to get rid of them not to be the same, I would immediately erase my step and do not multiply by 2. But in this case, when I multiply by 2, 4, 6, when I multiply by 2, I was getting different number all through my table, which makes it very, very perfect for what it is I want to do, right? So the next thing I want to look for now is our indices. So for our indices, remember I already taught us the steps. So the question now you want to ask yourself is, you need 3 numbers that when you raise them by the power of 2 and sum them up together, you get 2, which is 1 square plus 1 square plus 0 square, which will give me 1 plus 1 plus 0, and I get my 2. So my answer here is 1, 1, 0. Is that making sense? So for the next guy, what times what will I get? So if I say 2 plus 1, so 2 times 2 will give me 4. So I don't need the 1. I already know that my next answer is 2, 0, 0. Sorry, not 6. That was 0 actually, but it looks like 6. 2, 0, 0. The next guy is 2 raised to power 2. I have my 4. 1 raised to power 2. I have 5. Then another 1. I have 6. Perfect. Then for this guy, I know it is 2, 2, 0. That's 4 plus 4. For the next guy, I will just go ahead and say 3, 1, 0. That's 9 plus 1. Then this guy, I would say 2, 2, 2. Yeah, because I have 4, 4, 4. That's cool. Then for this guy, it's going to be 3, 2, 1. Then for this guy, it's going to be 4 times 4, which is 16. So now I just filled in these brackets, guys. So after filling these brackets, we still need to go ahead and solve some things. So from here, you can know the crystal structure. There are 2 ways of knowing the crystal structure. You can know from this table, from this portion of the table, you can know, and solving ahead when you have the same A's, when you have the same lattice parameter. By the time you begin to solve and you're getting the same lattice parameter consecutively, you know that, okay, yes, you are doing the right thing and you are on the right path. Before we jump into solving the lattice parameter, guys, let's compare. You come to this side of the table. Let me zoom in. So the first thing we had was 110. We have 110, right? The next thing we have, let me use red. The next thing we have is 200. We have 200. The next thing we have is 211. We have 211. The next thing we have is 222. 220, sorry. Then the next thing we have is 311. What convincing again do I need to know that this is a BCC structure? So I'm just going to go ahead and declare that, bro, this is a BCC structure. Alright guys, so I forgot to mention earlier that we were given, or we were told, that our wavelength lambda is equal to 1.5406 Armstrong. Right, we're given this in the question because we need it to find our interplanar spacing, which is D, or we need it to find our lattice parameter. Alright guys, so after being given our wavelength in the question, we know that our n, which is the diffraction order, is equal to 1. Right, sometimes you are told, most of the time you figure it out. So for our n being equal to 1, we apply it into this formula saying n lambda is equal to this. So 1 times lambda remains, so all we just apply straight is our lambda, which is Armstrong. I'm coming, sorry. Also guys, take note that this is also 0.15406 nanometer, right? Whichever one. So it's best you always solve in nanometer for. Alright guys, so let's make D the subject of the formula in this equation, right? So our D HKL is equal to lambda over 2 sine theta. Since our n is 1, so now we are going to choose 1D HKL, 1D, which will be this guy. So we are picking D31. So our interplanar spacing is D, or we're picking that of 7, right? So D321 is equal to our wavelength in nanometer 0.15406 over 2 times sine theta. So remember, this is sine theta, not sine square theta. So the theta under this place is 55.2, theta is 55.28. So we go ahead and divide it by 2. So 55.28 divided by 2 is going to be 27.64. 27.64. Right, so when I punch that into my calculator, I have 0.154006 over 2 times sine of 27 points yada yada. So my D interplanar spacing is 0.1660 nanometer, in which if I'm to convert it to Armstrong, it's going to be 1.6 Armstrong, right? So we just solved for that. We just found our D. So now that we know our D, we can go ahead and look for A for each and every one of them. So let me just erase. A is equal to our interplanar spacing, which is 0.1660 nanometer, right, times root 3 square plus 2 square plus 1 square, right? So let's punch that into our calculator. 0.6213 nanometer also. So we already found this. Now we can go ahead and begin to solve for each and every one of them. Okay, so let's confirm. Since we solved for that, let's use another interplanar. Let's use another line. I think we should use 400 now to find our D and look for our A again. So using D400, we say lambda, which is 0.15406 over 2 sine our theta is 59.42 divided by 59.42 divided by 2, we have 29.71. Yeah, so let's punch that into our calculator. Our answer is 0.1554 nanometer. So let's apply it for our A. A is equal to 0.1554 times, what's our HKL for that row? 4 square plus 0 square plus 0 square. Sorry. So answer times root of 4 square plus 0 square plus 0 square. Can you see? We derived at the same answer, 0.6213 nanometer. So seeing these two guys being the same thing, then we are definitely correct that the structure is VCC, because we are getting the same lattice parameter even after we solved for two different equations, right? So these two guys being the same thing, you can try it out on your calculator. Being the same thing, it is 100% certain that is BCC structure. So guys, drop a like, comment and subscribe to the YouTube channel. Thanks and bye.